Okay, so now uh, we have already discussed about exponential matrices, right, in our previous lecture. So if we just quickly recall, we had said that for a matrix, for a matrix A, supposedly square matrix, we can form the exponential of it, right? Exponential of it. So it's simply given as I plus A upon 1 factorial plus A squared upon 2 factorial plus A cube upon 3 factorial and so on. So we can simply write it as n equals to 0 to infinity A to the power n upon n factorial, where somewhat an obvious assumption that A to the power 0 is the identity of it. Okay. And using this, we had also said the fact that if you have some identifying scalar, say t, so e to the power ta is then simply it directly goes from definition, right? So it's ta whole to the power one eight. And one more thing which we had observed was that um, e to the power uh, p inverse a p. This was basically p inverse e to the power a, right? Because we have shown that this is simply summation n equals to 0 to infinity p inverse a p whole to the power n by n factorial, but the numerator is simply uh, so it's p inverse a to the power n, right, upon n factorial. Then you can just use the distributive law, inverse of the distributive law, to bring p inverse out from the left, p from the right, and I will do this. Was quite an obvious statement. We had proved these statements, and using this, it was easy to calculate e to the power a when a was a diagonal matrix. A was a diagonalizable matrix, I should say. A was a diagonalizable matrix. Because if A is a diagonalizable matrix, then there exists invertible matrix P, such that A, uh, A can be written as P d P inverse, right? If you recall, A can be written as P d P inverse. And then that would imply e to the power a is nothing but p e to the power d p inverse. And calculating the exponential of a diagonal matrix is very easy, because if suppose d is the diagonal matrix where the diagonal entries are lambda 1, lambda 2, and so on till say lambda n, then e to the power d is the matrix which simply contains e to the power lambda 1, e to the power lambda 2, and e to the power lambda. Okay. These things we have proved in the previous lecture. Our concern is that suppose you have a matrix A, which is not diagonalizable, and we are asked to find, let's say, e to the power a. Okay. Then what is the most possible, or I should say most favorable option uh, for a for a to be considered so that this calculation is easier? Now, in the previous lecture, I had given an introduction to Jordan decomposition theorem. So if I just write the statement here, then I'll explain it, and then I'll move forward to the Jordan decomposition theorem. So just explain the Jordan decomposition theorem. The Jordan decomposition theorem. What does the Jordan decomposition theorem simply say? It says that if I simply use a definition for a matrix, then uh, every complex n cross n matrix, is similar to a Jordan matrix. What is a Jordan matrix? So it's simply a matrix which is in block diagonal form, where each block is a Jordan block. So it's similar to a Jordan matrix, where the Jordan matrix or the Jordan form, this Jordan matrix is called the Jordan form for the matrix we talk about. So the Jordan form is unique up to the order of the blocks, up to the order of the blocks. Clear? Okay, so, and if we can also define this from a vector space point of view, we can say that let V be a finite dimensional vector space over C. Now we are talking about here about complex matrices. We are talking about here vector spaces over the complex space, just because to keep the underlying field algebraically closed, so that we can talk about the existence of every eigenvalue. So let V be a finite dimensional vector space over C. Then there and let T be a linear operator defined on V. Then there exists an ordered basis. There exists an ordered basis for V, say B, such that the matrix of T with respect to B is similar to a Jordan matrix. Is similar to a Jordan matrix, which is unique up to the order of the blocks, which is unique up to the order of the blocks. The order of the blocks. Okay. Now, what is important about this theorem? First thing first, this theorem speaks the fact that every matrix you consider over the complex complex field, then you will surely get a Jordan form to it. This is the first thing first. Secondly, it helps us to construct the basis or the matrix such that the similarity is witnessed. Try to say is that suppose A is a n cross n complex matrix. Okay. Then by the Jordan decomposition theorem, A is similar to a matrix JA, but this is the Jordan matrix. Okay. Now we know from the definition of similarity, this typically means that there exists invertible matrix. There exists invertible matrix P such that AP is equals to P, or A is equals to P, J, A, P, whatever you want to speak of. Clear? So this theorem also helps us to construct this P, construct out this P. Okay. What is the usefulness of having this P? Observe that if you are asked to find the exponential of it, then e to the power is e to the power p j a p inverse. E to the power p j a p inverse is p times e to the power e j a p inverse. Now this is a block diagonal matrix, right? This is a block diagonal matrix. Okay. What is the importance of exponential of a block diagonal matrix? Suppose you have, one sec. Suppose you have B to be a matrix which is of this form. Let's say it has B1, B2 till Br, where each of these are matrices. Okay. Then e to the power B is the matrix considering the blocks e to the power B1, e to the power B2, and so on till e to the power Br. Okay. Again, these are also matrices, right? Therefore, e to the power Ja it's a block diagonal matrix, right? So if Ja is a block diagonal matrix, since Ja is a block diagonal matrix, so Ja is somewhat of this form. We can say it's J1, J2 till say some Jk. Then e to the power Ja can be easily considered as the matrix e to the power J1, e to the power J2, and so on and so forth till e to the power j, right? Okay. Now, if you have, uh, suppose we choose a Jordan block, for example. Suppose we choose j lambda as a 3 cross 3 Jordan block. Let's see, you have this. So this is one, this is one. Observe that we can write it like this. We can write it as lambda, lambda, lambda plus. We can write it as 0, 1, 0, 1, 0. Right? Observe that these two commute. Observe that these two commute. So since these two commute, therefore any power of j lambda to the power r, then that was, so suppose this we represent as d, this we represent as say, n. So j lambda to the power r is d plus n whole to the power r. But we can obviously use the binomial expansion in this case. Right? We can use the binomial expansion in this case. So we can expand this as summation n equals to 0 to r. We write it as r c n d to the power r minus n to the power. Right? Right. Now calculating the powers of d is a very easy task. So any power of d, so lambda, 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 if you have in the diagonal, or any diagonal matrix if you have, then the each individual element in the diagonal entry does just you know rises by the same power, and the matrix n is also in a very simple state. You can also calculate the powers of it. So this indeed helps in calculating the power of j lambda. If you have calculated the power of j lambda, then calculating the exponential of j lambda becomes also easier, because e to the power j lambda is simply by definition summation j lambda to the power n over n, right? So if you have calculated the exponential of each of these j lambdas, then you can calculate the exponential of e to the power j. If you have calculated the exponential of e to the power j, then the matrix you started working with, so it's simply p inverse, sorry, p, I guess p e to the power j a. It was like this, right? So it's p e to the power j a, right? Clear from here? Okay. Got it? So first thing what we do is that we prove the Jordan decomposition theorem as much as we can, and then we will be showing some applications of it. Okay. So proof of the Jordan decomposition. So let's start the proof. Now the proof is a bit long, so we divide it into 4 steps, and the proof is due to Filipov. Okay. So what we do is that we use induction over the dimension of V. So we are proving this for the vector space, then it will automatically get proven for the matrix as well. So we are using the vector space definition for Jordan decomposition theorem, and what we do is that we induct on the dimension of. Why do we do this? Because if we induct on the dimension of S, so it allows us to assume that the theorem is true for some for the restriction of T to any proper T invariant subspace of T. Okay. So this allows us to assume that the statement holds. The statement holds for the restriction of T. T is obviously the operator for the restriction of T to any proper T invariant subspace, to any proper T invariant subspace of V. Okay. Now, if V is the direct sum of these property T invariant subspaces, if V is the direct sum of these T invariant subspaces, these T invariant proper subspaces, then let's say V1, V2 are the proper T invariant subspaces, Vr are greater than 1. Then, since the statement holds for each of these Vi's, then the statement should hold for V as well. Then the theorem holds for. Okay, so this is basically the step one, where we are explaining our procedure. Okay. Next, what we do, it's very simple. We choose a generalized eigenvector. Suppose, now to understand the theorem from here, you need to view the lecture previous to it, because there I have explained one proposition and one lemma, and the terminologies used in that proposition and lemma will be continued throughout this proof. So suppose we have, and I have named the proposition and lemma as proposition 1 and lemma 1, so I will just refer to them as proposition 1 and lemma 1. Suppose we have generalized eigenvectors Vi, I equals to 1 to R. Let capital Vi be the subspace defined as in proposition 1. Defined as in proposition 1 with x equals to Vi. X equals to small. Okay. If V is the direct sum of these subspaces, so if x is this, if V is the direct sum of V1, V2, so on and so forth till Vr, then the theorem is true for V. Then the theorem is true for V. And these generalized eigenvectors, these vectors small v1, small v2 till small vr, these are called the Jordan generators. These are called the Jordan generators of T. Sorry. Okay. So what we basically show is that we show that these Jordan generators exist. We show that Jordan generators exist. Clear? One second. Okay. So what is the basic thing which we have already learned from this statement is that the uh, the basis with respect to which T will consider the Jordan form will be typically dependent on the eigenvectors corresponding to each eigenvalue. What I mean to say is that, let me just give a brief hint to it. What I mean to say is that, suppose you have a Jordan block where lambda is an eigenvalue, and suppose this is a 2 cross 2 Jordan, just simply by a numerical example, 2 cross 2 Jordan block. Then for a supposedly for a linear operator for which a certain basis exists, such that the matrix of that linear operator is just Jordan block, then that basis will consist of two vectors which are generalized eigenvectors of exponent 1, sorry, of exponent 2 corresponding to this eigenvalue. So it will be V and say T minus lambda I If it was a 3 cross 3 Jordan block, then the basis would be V T minus lambda I V T minus lambda I squared. Okay, we need to find this vector only, and the rest is very obvious. Okay, so if we have a so the basic thing what happens is that suppose we have a Jordan matrix where we have Jordan block, say J lambda. Suppose we take J lambda 1, J lambda 2, J lambda 3. Then for J lambda 1, suppose J lambda 1 is a D1 cross D1 block. J lambda 2 is a D2 cross D2 block. J lambda 3 is a D3 cross D3 block. Then the basis element uh, for J lambda 1 will be consisting of a generalized eigenvector of exponent D1 with respect to the eigenvalue lambda 1. So it will be V T minus lambda 1 of V. T minus lambda 1 means T minus lambda 1 I, and so on till T minus lambda 1 to the power D minus 1, D1 minus 1 to the power D1 minus 1. So J lambda 2, it will consider some let's say U T minus, so this is lambda 1, right? So T minus lambda 2 of U, and so on till T minus lambda 2 to the power D2 minus 1 of U. And say J lambda 3 will be W T minus lambda 3 of W, so on till T minus lambda 3 to the power D3 minus 1 of W. Then what will be the final basis for V? The final ordered basis for V should be these arranged accordingly according to the block. So we have J lambda 1, so we put this first. So we have first the basis, suppose we write it as B J lambda 1, B J lambda 2, B J lambda 3. So we have B J lambda 1, B J lambda 2, B J lambda 3. And the matrix P, the columns of P, the P matrix for this J, that is, suppose you have a matrix A which is similar to J. Then this matrix P such that A is equal to Pj P inverse. This P along the columns which contain these vectors sequentially as they appeared in the blocks. Okay. So you will have B J lambda 1, B J lambda 2, and B J lambda 3 column wise, and this will give you the vector. Okay. Let us quickly take an example. Let's quickly take an example. Suppose you have the matrix A, let's say. Suppose A is 0, 1, minus 4, 4. Okay. What are the eigenvalues of it? So, we consider lambda I minus the determinant of this. So, it's coming out to be, say, x minus 1, 4, x minus 4. So, it is x times x minus 4 plus 4. And this is x minus 2 whole square. So, the eigenvalues of A are 2, 2. Clear? So, first let us calculate the Jordan block. How to calculate the Jordan block? We just need the geometric multiplicity so for suppose lambda is an eigenvalue of a certain matrix A. Let me just also explain this fact. Suppose lambda is the eigenvalue for some matrix A, then the algebraic multiplicity of lambda, this gives the total number of occurrences of lambda in the Jordan form. and the geometric multiplicity of lambda. This gives you the number of Jordan blocks associated with lambda. Okay. So we have the algebraic multiplicity of 2 in this case. So it's 2. A is indeed a 2 cross 2 matrix. So the Jordan form A will be similar to will also be 2 cross 2 obviously. Therefore, the total occurrences of, so 2 is the only eigenvalue precisely. So the Jordan form will contain along the diagonal only the eigenvalue 2. What we need to calculate is what is the total number of blocks for 2. If there exists 2 blocks for 2, then A will become a diagonal matrix. Because what are the possible 2 cross 2 blocks? What are the possible 2 cross 2 Jordan blocks? One is this one. If you have 2 blocks, so lambda, lambda, lambda 1, lambda 2, let's say, whatever. And the single block will be like this, right? What is the geometric multiplicity of 2? So this is nullity of A minus 2i. So now calculate A minus 2i. A minus 2i will be precisely minus 2, 1, minus 4, 2. Observe that it's similar to minus 2, 1, 0, 0. Right? Therefore, the nullity of A minus 2i is indeed 1. Therefore, there should exist only one Jordan block. So that means this should be the matrix. Right? Therefore, A is similar to the matrix 2, 2, 1. Right? Therefore, the obviously since A is similar to this, there exists eigenvalues. There exist eigenvectors. I should precise, or let me not talk about this in this way. There exists invertible matrix, let's say, P such that A is equal to P J P. This is J. How to calculate P? We need to just find a basis. How do we find a basis? We need to just find a vector V. So since the Jordan matrix is a single block, which is a 2 cross 2 block, and it's as a whole a Jordan block corresponding to the eigenvalue 2. So the basis, Jordan basis, or the Jordan generator will be an eigenvector of exponent 2 corresponding to the eigenvalue 2, right? So let us consider the example, the vector as E1, let's say E1, 1, 0. Then what is A minus 2i of E1? So it's A minus 2i of E1 is it's minus 2, 1, minus 4, 2 times 1, 0. So it's basically, so we have minus 2 here and we have minus 4, right? Right. What is A minus 2i squared of E1? Then this will be A minus 2i times this vector minus 2, minus 4. So it's precisely minus 2, 1, minus 4, 2 times minus 2, minus 4. This calculation gives you 0 because it's minus 2 times minus 2 plus 4 and minus 4 is 0. Minus 4 times minus 2 plus 8 and minus 2 and 2 times minus 4 minus 6. 0. Therefore, we can consider P, but the columns contain these elements, right? E1 and A minus 2i of E. So the matrix P will come out to be of the form 1, 0, minus 2. Let's calculate AP. Let's calculate AP. So what is AP? So what is A given? A is 0, 1, minus 4, 4. And P we have got 1, 0, minus 2, minus 4. So this is basically 0 times 1, 1 times 0, 0. 0 times minus 2, 1 times minus 4, minus 4. Minus 4 times 1, minus 4 times 1 and 4 times 0, minus 4. And here you have minus 4 times minus 2, so it's 8. And minus 16, so it's minus 8. Okay. Let's calculate Pj. We already have J. So what is Pj? So Pj is, what is P? P is 1, minus 2, 0, minus 4. and j was 2, 2, 1, 0. Let's calculate this out. So it's 1 times 2 and here you have minus 2, so 0. 1 times 0 and minus 4. Here you have 0 times 2 and minus 4 times 1, so minus 4. You have 0 times 0 and minus 4 times 6, so it's minus 8. Right? Therefore, it's quite obvious from here that AP equals PJ. P is clearly invertible. The determinant of P is minus 4, so it's clearly invertible. That means A is PJ. Clear? Got it? Okay. So this is the way it typically helps. Now this is the procedure you can think of. Observe that suppose, let me think of this in this way. Let us consider another example. One second. Let us consider another example. I'll not explain that, but I will just give a brief of the concept. Okay, let us consider this example. Say the matrix B is given as 1 minus 1 1, 2 minus 2 2, minus 1 1 1. Okay. What are the eigenvalues of B? So xi minus a is what we need to calculate. Okay. So let's check xi minus b. So it's x minus 1 1 minus 1. Here you have minus 2 x plus 2. Here you have minus 2. Here you have 1 minus 1 x minus 1, right? X minus 1 1 minus 1, minus 2 x plus 2 minus 2, minus 1 becomes plus 1, so plus 1 minus 1 x minus 1. Okay. So what will it be? So it's x minus 1 times, you have here x plus 2 times x minus 1, right? So you have x plus 2 times x minus 1 minus 2, minus you have, so you have minus 2 times x minus 1, that is 2 minus x, and here you have plus 2, right? So it's minus 2x plus 2, correct? Okay, and then you have plus, in this case you have 2 minus x minus 2. So this is my x minus 1 times this becomes x squared. This is plus 2x minus x. So plus x. Here you have minus 2 and minus 2. So minus 4 minus what do you have here? You have here 4 minus x. Right? And here you have minus x. Right? So let me just so yeah. So we calculate it here. I don't want to go to the next page to continue the calculation. So this is x minus 1 times x square plus x minus 4. So this becomes minus 4 plus x minus x. So it becomes minus 4. Right? So it's becoming minus 4, right? Okay. Okay, then you need to calculate this out. So this will eventually, am I doing it correct? This is a very long calculation. So this is x cubed plus x square minus 4x minus x square minus x plus 4 minus 4. So this part cancels out, right? So what are you left with? You are left, you can take x common outside. So you have x squared plus x. Yes, about this question. You have x squared plus x, x squared plus x minus 4. Then here what do you have? You have minus x, and here you have minus 1, right? Right? Correct. So you take x common outside, so you have minus 5x here. Yeah, this is correct. I haven't done any mistake out here, right? X plus 2 times x minus 1. It's 2x minus xx here. Okay, rest parts cancel out. So you have x times x squared minus 5, I guess. Is this what you're getting? Okay, let me do it fresh in the next page. Yeah, you have b is equals to 1 minus 1, 1, 2 minus 2, 2, and minus 1, 1, minus 1. Right. So we need to calculate the eigenvalue. So the determinant of xi minus p. So determinant of x minus 1, 1, minus 1, minus 2, x plus 2, and this is minus 2. Then you have your 1, minus 1, and you have your x plus 1. Right? Right? Okay. So, yeah. Let me just calculate it out from the computer itself. Because it's going to be a long, it's coming out to be a long problem. Let me just, so you have the matrix as 1, minus 1, 1, right? 1, minus 1, 1. Then here you have 2, minus 2, 2. You have 2, minus 2, 2. And here you have minus 1, 1, minus 1. Right? 1 minus 1. So let's check what should the characteristic polynomial should be. Okay, so it's coming out to be minus lambda square times lambda plus 2. I have done some mistake here, some horrible mistake out here. Okay, I'm very sorry. Yeah, so it's coming out to be minus x squared times x plus 2. Okay. Okay. So what are the eigenvalues? The eigenvalues are 0, 0, and 2. Right. Let us first calculate the Jordan form using the geometric multiplicity. So in the Jordan matrix, 0 must appear in total twice and 2 must appear in total once. What are the number of Jordan blocks with respect to 0? First, let us calculate. So what is the geometric multiplicity of 0? Okay. So what is A is given as 1 minus 1, 1, 2 minus 2, 2, minus 1, 1, minus 1. What is the nullity of A? So it's so you have 1, 0, 0. Sorry, you have 1 minus 1, 1. Then the second can be row reduced to 0, 0, 0, and the third can also be just added with row 1, right? So you get 0, 0. So the nullity of A, which is same as the nullity of A minus 0 I, so it's coming out to be 2. Therefore, there are in total 2 Jordan blocks for 0. There are in total 2 Jordan blocks for 0, right? And the Jordan block for 2, that should be precisely 1, right? That's quite obvious. So the matrix should come out as 2 Jordan blocks for 0 and 1 Jordan block for 2. So 2 Jordan blocks for 0 and 1 Jordan block for 2. Okay. So it's a diagonal matrix. It's a diagonal matrix. Whatever, indeed a Jordan block. How to calculate the basis? So you need two basis elements for 2. You need two basis elements for 0 and one basis element for 2. So you need to calculate a vector V such that V is a generalized eigenvector associated with 0, the eigenvalue 0, of exponent. So in this case, what should be the exponent you require? So you need exponent 1 here. Right? Right. Am I doing this correct? Just check once again. The nullity of A is is 2 times this plus this, 2 times this minus this will become 0, right? Indeed. And this plus this will also become 0. Yeah. So this is a diagonal matrix, right? So you just need to place the eigenvectors for 0 and 2. That will do. It's a very easy example. Let us consider one more example. I just wasted a lot of time for a very, very bad example. I'm very sorry. Let's consider this example. 0, 1, 0, 1, 0, 1, 0, minus 1. Okay. Then what is the characteristic polynomial for this should be? Okay. Let us just quickly calculate it out. You have 0, 1, 0. You have 1, 0, 1. And you have 0, minus 1 and 0. Right? Yeah. So the characteristic polynomial, what should it be? So this should be, I get x cubed. Okay. So you have eigenvalue 0, 0 and 0. Right? What are the number of Jordan blocks? I should consider that. So what is the nullity of A? The nullity of A is so you have 0, 1, 0, right? On see, you can obviously observe it from here that A is row equivalent to the matrix which has only 1, 0 row. The nullity of A is precisely be 1. Therefore, there must exist only one Jordan block. One Jordan block for 0. And that will obviously be a 3 cross 3 Jordan block. So we have J to be equal to a 3 cross 3 Jordan block for 0. So it's 0, 0, 0, 1 and 1. This should be similar to. Okay. Okay. Now we need to consider a vector V in order to form the basis such that V is a generalized eigenvector associated to the eigenvalue 0 of exponent 2, exponent 3, right? Because it's a 3 cross 3 Jordan block. Got it? Let's choose E1 first. Okay. Then what is A times E1? So A you have is 0, 1, 0, 1, 0, 1, 0, minus 1, 0 times E1. Right? Here E1 will be 1, 0, 0, right? So what they will give us? So you have 0 times 1, 1 times 0, 0 times. So you have 0 here, 1 times 1, 0 and 0. So 1 here, 0 times 1, minus 1 times 0, 0 times 1. You have 0 here. Precisely E2. Okay. Then what is A squared E1? So A squared E1 is A E2. So let's calculate. So you have 0, 1, 0, 1, 0, 1, 0, minus 1, 0 times E2, 0, 1, 0. So it's 0 times 0, 1 times 1, 0 times 0. So you have 1 here, 1, 1 times 0, 0 times 1, 1 times 0. 0 here, 0 times 0, minus 1 times 1 and 0 here. So minus 1. Okay. Then what is A cubed of E1? So it's typically 0, 1, 0, 1, 0, 1, 0, minus 1, 0 times 1, 0, minus 1. So 0 times 1, 1 times 0, 0 times minus 1, 0. 1 times 1, 0 times 0, 1 times minus 1, 0. 0 times 1, minus 1 times 0, 0 times 1. Yeah, so it's 0. So E1 will suffice, right? Therefore, the basis, the Jordan generators, I should say, is E1, A E1, A squared E1. So if you just consider the matrix P as E1, A E1, A squared E1, so which is the matrix 1, 0, 0. A E1 came out to be 0, 1, 0, and A squared E1 is 1, 0, minus 1. Then this will be your matrix such that A is equal to P. What was J? J was 0, 0, 0, 1, 1 times P. Right? Okay, so I guess it's enough for today. In the next lecture, we will give the complete proof for the Jordan decomposition theorem, and then we will be solving some corollaries or talking about some relations between a Jordan form or the Jordan decomposition theorem and the diagonalization of a matrix. Okay, so meet you guys in the next lecture.